Hi, welcome to tutorial 6.3 part 1. This is the first of 3 tutorials on the Bohr atom. What we're going to do in this tutorial is just get used to 2 equations. One that can be used to figure out the radius of an allowed orbit in a hydrogen atom according to the Bohr model. And then also the second part is how much energy does that electron have when it's in one of those allowed radii. So right now we're going to try to stay real concrete, not worry so much about exactly the derivation, but just kind of what the result is so we can get our bearings. Here is a picture, just some circles that are supposed to represent orbits of where an electron is allowed to exist in the Bohr model of a hydrogen atom. So these are not different individual electrons existing in these orbits, but these are the possible orbits that one electron, that is the one electron in hydrogen, can occupy depending on how much energy it has. So this inner ring is the closest that an electron can be. It can exist stably in that particular location, or in this further ring out, that would be the other radius that it can exist in, the other radii. Each of those will be associated with numbers. We're going to associate this one here with the value n equals 1, this one n equals 2, n equals 3, referring to the different orbits. Look at the sense of scale. We're at an angstrom level here. This is all times 10 to the minus 10 meters. All right, so these are the different individual orbits that a single electron in a hydrogen atom can occupy according to the Bohr model on the assumption that angular momentum is quantized. What are these numbers? These numbers are the energies associated with the electron in those various orbits. Now, you might be a little confused here about the negative numbers. You say, well, why do you have like a negative 13.6? Why are all these numbers negative? When we normally think, say, of a potential energy of an object that's above the Earth, and we say how much potential energy does it have? Let's say we have 1200 joules, and then as you get closer to the Earth, we tend to say you're losing potential energy, turning it into kinetic energy, and finally the reference frame we typically use is that the surface of the Earth then has 0 potential energy. It doesn't, it's just a reference frame. So that's what we're used to, large numbers of potential energy, that is like 1200 joules, turning into 0 when you hit the ground. This works the same way, but instead of having the large number out here like the 1200 joules, we say out here the electron essentially cannot feel the attraction of the nucleus, and as it loses potential energy on the way down, it finally loses all the way up to 13.6 in the case of hydrogen. So out here the electron has 0 potential energy. It can't feel the nucleus at all. Down here it drops, it loses 13.6 to arrive at that lowest orbit. Okay, that's the energy values and the radiuses. Let's just see if we can now get a little sense for these numbers. So what are these numbers here? N, 1, 2, 3, 4, 5, 6. These are the different orbits. This is the closest orbit when you're really close to the nucleus. That's n equals 1 orbit. This means the second orbit, third, fourth, fifth, and sixth. And look at these radiuses. The numbers should kind of make sense. They look like they're squares of each other. So the closest you can get in to a nucleus is 0.529 times 10 to the minus 10, according to the Bohr model of the hydrogen atom. The second orbit is about 4 times as far. So this is 4 times as far as this particular distance. This is roughly 9 times as far, 16, 25, and 36 times as far. And that drawing showed it on the other side. How much energy is associated with these various orbits, that is how much energy is associated with the electron at those orbits. These are the numbers that are given here in electron volts. That's when you're in, that's all the energy that you've lost to getting really close to the nucleus. This is the little bit that you would lose just to drop down from not feeling the electron down to that 6th orbit. These are just the same numbers in joules. So what we want to do right now is just derive a couple of these, or just calculate out a couple of these values, so you're not just looking at a table of numbers, but you can see how they're arrived at, and if you watch those other 2 videos, how they emerge from the assumption that Bohr made about the quantized nature of angular momentum. Alright, so let's look at one. We're going to do 2 of these for the 5th and the 3rd orbit. Let's just see if it makes sense. Question, if you're over here in this 5th orbit, where are you? What's your radius? And if you're out here, how much energy do I have associated with you as an electron in a hydrogen atom? The radius first, let's have a look at that one. The equation is straightforward. All of the radiuses are simply multiples of this constant value, the closest radius that you can have, 0.529 times 10 to the minus 10, that's the radius when you're in as close to the nucleus as possible. Since we're in the fifth orbit, we say the equation tells us that we have to take the fifth orbit and square it. That's this integer value based upon the quantization of angular momentum. And we multiply the two and we get the orbit. So we get 13.2 times 10 to the minus 10 in the fifth orbit. So let's kind of go back and look at that from that chart. That's where we came up with this number here, 13.2 times 10 to the minus 10. That's the radius of one of the allowed orbits in a hydrogen atom. That is the fifth orbit for hydrogen. All right, let's go back now. Once we know the radius, can I figure out the energy? What's the equation for that? The equation is simply the lowest energy that you can have. That was when you've collapsed and you're completely down by the nucleus. That's negative 13.6 divided by the orbit that you're in squared. So the negative 13.6 divided by 25 comes out to minus 0.544 electron volts. And we can convert those into joules by multiplying by 1.6 times 10 to the minus 19. Let's go back, look at the table so you see the values sitting there. There the value is here. It has one less significant figure here, but it's the same number. In the fifth orbit, this is how much energy you have in electron volts, or if you convert it into joules, this is the number in joules. So I hope that felt okay. All we're doing here is saying, look, at least I can figure out where these numbers came from, and I can see where these equations came from based upon Bohr's assumptions. So let's just do one more so we know we feel comfortable with the idea. Let's try the third orbit. Same exact thing. If I'm in the third orbit, what is my radius? I have to multiply the 0.529 times 10 to the minus 10 times the orbit that I'm in squared. Same constant. Times 3 squared comes out to this radius. That's where I am. That's not as useful to us, but I'd like to know how much energy I have when I'm sitting in that third orbit. How do I do that? I take the energy, the negative 13.6 electron volts, and simply divide by the orbit that I'm in squared. I have the energy associated with that third orbit, and this is the same number in joules. Okay, so all we're doing right now is playing with some equations, just typing in a few numbers. You're going to see the payoff. You're going to see how this allows us to figure out how electrons are structured in a hydrogen atom, how these various orbits make sense in terms of a structure of an atom. So be a little bit patient for now. Just get used to the calculations. We're going to do another set of these for the next 2 sessions, and you'll start seeing how all this leads to kind of a concrete result. All right, good luck with playing with these numbers, and we'll practice this in class. Thanks.